In this video, we're going to take a look at linear functions and their graphs. Now, linear functions and linear equations in this chapter will usually be written as one of the following. As a function, we write it as f of x is equal to mx plus b, usually. And as an equation, we write it as y equals mx plus b. So as a function, we use function notation. Um, as an equation, just in x and y, a lot of times we write it with just y equals. Again, this is also an equation, but this is function notation. These two things are going to be essentially interchangeable, just with different notations. Now let's start out by asking ourselves what makes something linear? Well, there's a couple of ways to go about this. One thing that we can do is we can say a linear function can always be written this way. Y equals mx plus b. Or we could say a linear equation can always be written this way. A times x plus b times y equals c. These are very common equations for linear equations. Now, in both of these types of equations, whichever way I write this, I want you to notice that the variable x and the variable y are being raised to the first power. Also, those two variables are not being multiplied times each other. And lastly, when I say raised to the first power, I mean raised to the first power if I write the variable in the numerator, or I'm not writing the first power in the denominator. I'm not writing m divided by x, for instance, or I'm not writing b divided by y. So when I write everything out in one of these two ways, I get variables raised to the first power, and then the variables are not multiplied by each other when I force those variables to be in numerators. Let's take a look at the following equations and determine if they are linear or not. I'm going to write all of these down. So that we can have the record. So here we go. 9x minus 6y equals 10. Notice that both of those variables are raised to the first power implicitly. Therefore, this is a linear equation. In the second one, 5x squared minus 2y equals 17. That is obviously not linear because we have an x squared component there. 5x equals 4 divided by y is also not linear. And again, you might say, well, aren't x and y both being raised to the first power? Well, they are, but technically I could have rewritten that where that y on the right-hand side goes into the numerator. So I write it as 5, I could have written this as 5x times 4 times y to the negative first power. And if I write the y in the numerator, I get y to the negative 1 power. So that is not linear. That's one of the trickier things. And that's what I was talking about by saying we want to make sure our variables are in the numerator raised to the first power. This one is not linear because this x is underneath a square root. And again, if I rewrote this, I could write this as y is equal to the square root of 5, and then I could pull x out and raise it to the 1/2 power or to the 0.5 power, and then plus 3. So if I wrote it outside of the square root, that would be x to the 0.5, and therefore this equation is not linear. This equation with 4y plus 7x plus 10 is equal to y minus 2x plus 13 is in fact linear. All of our terms are dealing with y and x being raised to the first power. They're all in the numerator. They're all not under any square root or anything like that. So this is linear. And if we wanted to rewrite this like one of those other equations, we could subtract y from both sides. We could add 2x to both sides. So we could rewrite it in that case. Y squared is equal to 16 times x squared. That is not linear either because we have x squared and y squared. Again, sometimes you may think, well, could I take the square root of both sides? You kind of could, but remember, if you take a square root of something, we have to consider both the positive and negative square roots. So this is not linear either because of the x squares. So you can see when an equation is linear and when it's not. One of the first things we're going to do with linear equations and linear functions is to graph them. Now, the graph of a linear function in two variables, or the linear equation in two variables, is going to create a straight line in the Cartesian coordinate plane. So if we graph y equals mx plus b, we should end up with a straight line. That's the nice thing about having a linear function or a linear equation in two variables. The first way we're going to graph is by our standard finding points on that line. In other words, finding points that make this equation true. Let's do an example. Let's graph the following line by finding points. So here we have y equals negative 2x plus 5. We're going to find some points that make that equation true and then graph them and then basically connect the dots and extend that to graph the entire line. I'm going to create a table here to help me do that. Generally speaking, when I have a line written this way, I have a linear equation written this way, what I'll do is I'll start by plugging in x values, and then I just have to evaluate the right-hand side to get the corresponding y value. So I might plug in an x value of negative 2. And if I do that, negative 2 times negative 2 gives me a positive 4, plus 5 gives me a y value of 9. If I plug in a negative 1, then what I end up getting is a positive 7. If I plug in a 0, then what I end up getting is a 5. You can check these on your own if you like. If I plug in a 1, I end up getting a positive 3. And if I plug in a positive 2, I end up getting a positive 1. So this gives me 5 different points, 5 different ordered pairs, which make this equation true. And we'll see that when we plot these ordered pairs on my Cartesian coordinate plane, they form a pattern. Let's go ahead and plot those points. So the first ordered pair was -2, 9. That's right here. The second ordered pair was -1, 7. That's right here. Then 0, 5. Then I had 1, 3. And then I had 2, 1. And we can see the pattern here. It's going to, when I connect the dots and extend that pattern, what we're getting is a straight line. It would be straight if I drew it straight, obviously. And that pattern goes on forever, to the right and forever to the left. And so that's how we could graph by plotting points. Now, as always, you could have typed in y equals -2x plus 5 into either the TI-84 or into Desmos like this and graphed that same line. Obviously, it goes through all of the points that we mentioned. The 0, 9, the negative, it's not 0, 9, -2, 9, -1, 7, 0, 5, 1, 3, and 2, 1. And we could have gotten lots and lots of other points as well. In fact, every single other point on this red line would make the equation true. Let's do another example. Let's graph this line by finding points. Again, notice that we're using the terminology linear equation and line sort of either, we can use either way. We can use either terminology of linear equation or line. So we'll graph the following linear equation or the following line by finding some points. Push pause on the video if you want to try this on your own. So I've set up a table, again, just to help me keep track of the organization, but I'm going to plug in whatever values I want in for my X. So maybe I'll plug in a value like -3. I could plug in a value like -1 as well. I want to show you sort of the difference between plugging in a -3 in this case and plugging in a -1 in this case. If I plug in a -3, I'll get 1/3 times -3 minus 4. That 1/3 times -3 comes out to a -1. So -1 minus 4 gives you a y value of -5. Hopefully everybody is understanding where I'm getting those values. I'm simply plugging in a -3 in for my X and then simplifying that right-hand side. When I simplify that right-hand side, I end up with a -5. And that means the graph of this function goes through the point -3, comma, -5. And that's what's happening on my table. That's what I'm putting into my table here, just the -3 and the -5. Well, if I plug in a -1, 1/3 times -1 minus 4 becomes -4 and a third. So I get that my graph goes through the point -1, comma, -4 and a third. Or you could write that as -13/3 as well. Doesn't matter. When I graph, I tend to like using the mixed numbers. Now, when I go to graph this point, -1, comma, -4 and a third, it's actually not going to end up as a really great point to graph because it's in the middle of my grid. And I kind of like it when these y values and the x values are integer numbers. In order to get an integer out in this case, notice that we did get an integer out when we plugged in a -3. In fact, because we have the denominator of 3, any number which is a multiple of 3, 3 times something, would give us out an integer value. So for my other x's, I'll probably just plug in multiples of 3. So 0 is 0 times 3. Plugging in 0 gives me a -4. If I plug in a positive 3, 3 is 3 times 1, I get out -3. If I plug in a positive 6, what happens is I get out a -2. And if I plug in a 9, I get out a -1. So plugging in multiples of 3 were kind of nice in this case because by doing that, it would cancel out my denominator when I multiply. Here we have lots of points that we can plot. So let's go ahead and do just that. We'll plot those points on the Cartesian coordinate plane and then connect the dots. Now I've plotted all those points already in Desmos. We have -3, -5, -1, -4 and a third, 0, -4. Then I did 3, -3, 6, -2, 9, -1. And we can see that the pattern for this line is doing this. I would connect all those dots, extend it, and then that line is just written here. So this is the line we get when we graph the linear equation y equals 1/3 x minus 4. Both the equation in example 2 and the function in example 3 had this form of y equals mx plus b. That form that we've looked at now a couple of times is actually called the slope-intercept form of a line. Now, it's called the slope-intercept form because when I write a line this way, the value of m gives me the slope of that line. And the value of b gives me the y value of the y-intercept. The y-intercept is obviously where the line crosses the y-axis. So 0 comma b is the y-intercept, and m is the slope. And those two values we can clearly see from this line if it's written in this way. And we can actually graph a line using the slope and the y-intercept. The way we do that is that we plot where the y-intercept is, and then we use slope to find the other points. Now, I haven't mentioned slope a lot yet, but slope of a line is the ratio of the change in the y value to the change in the x value, going from one point to the next. So we think of slope as change in y divided by change in x. Let's examine the slope in the last example that we did. Well, actually, let's start with the y-intercept first. The last example we did was y equals 1/3 x minus 4, or we could have written f of x equals 1/3 x minus 4. It's the same thing. My y-intercept is the point 0, -4. Now, the next point that we plotted was the point 3, -3 after the y-intercept. And I want you to notice how my graph changes from 0, -4 to 3, -3. If I want to travel from 0, -4 to 3, -3, I would say we need to go up one value in y and right over 3 values in x. Therefore, the change in y is going to be 1, and the change in x is going to be 3. So the slope of this line is 1/3, which happens to be that number out in front of our x. Now, this phenomenon doesn't just work for these 2 points. If we go from 3, -3 to 6, -2, we also go up 1 over 3. So slope of 1/3. But also if we go from 3, -3 to 9, -1, we would have gone up 2 and over 6. Well, the fraction 2 over 6 is the same as 1/3. Therefore, again, slope is 1/3. 2 over 6 is 1/3. And even in going from -1, -4 1/3 to 0, -4, we had to have gone, if I zoom in, we would have went up 1/3 and over 1. 1/3 divided by 1 is still 1/3. So the slope there is 1/3 as well. Any 2 points on this line, if I look at the change in y compared to the change in x, we get this fraction or the slope of 1/3. And so that's what the slope is telling us. Now, in our previous equation, we had y equals -2x plus 5. Obviously, we could see that that line went through the point 0, 5. And what happened there, well, let's look at the next point on that line. One of the next points on that line is 1, 3. Notice to get from 0, 5 to 1, 3, we'd have to go down 2 units in the y direction and over 1. So -2 divided by 1 is a slope of -2. And the same thing is true if we took any other point. Here's another point, 2.5, comma 0. We would have had to have gone down 5 units and then to the right 2.5 units. So that's -5 divided by 2.5. -5 over 2.5 is slope of -2. And what we're saying is that if we know the slope and we know a y-intercept, then we can plot the y-intercept and then use the slope to get to other points. And that's precisely what we're going to do by graphing using the slope and y-intercept. We'll plot the y-intercept and then we'll use slope to get to some other points, and then we'll connect the dots. Let's do an example. Let's take f of x is equal to 2 times x minus 7. This is in slope-intercept form, y equals mx minus 7. And because it's in this form, we can see that the y-intercept is going to be 0, -7, and the slope is going to be 2. The y-intercept is pretty straightforward. If you ever want to find the y-intercept, you just plug in 0 for x, and plugging in 0 for x gives you a -7. So -7 gets you there. I say that the slope, the m, the coefficient of our x, is 2. When I actually go to graph this, I want to think of this as change in y over change in x. So I'm going to use an improper fraction usually when I do slope, or maybe a proper fraction if one exists. But this is the change in y divided by the change in x. So the change in y is a 2, and the change in x is a 1. All right, so I've already plotted the point 0, -7, and I know that the slope is 2, or 2 over 1. So here's 0, -7. Knowing that the slope is 2 over 1 means I go up 2 in the y direction and right 1 in the x direction. So I know my graph should also go through the point 1, -5. Now I can be at 1, -5 and also go up 2 over 1. So another point on this graph should be 2, -3. And then from 2, -3, again, I go up 2 over 1, and I get to this point, which is 3, -1. And then I do the same thing, again, up 2 over 1 again. And you can see the pattern as we continually go up 2 over 1, we get this pattern. If I was drawing this by hand, I'd draw as straight of a line as I could between all of those points, and then extend that pattern out forever. For this case, all I'm going to do is I'm going to use the graphing feature to draw my straight line. And that's what we get. So if I were to graph this, y equals 2x minus 7, that's one way we could graph this by hand, is plot these points using the y-intercept and the slope, and then connect all of these points together, extend that line forever to the left and forever to the right. Let's do another example. Here we have example 5, which asks us to graph y equals negative 1/2 x minus 1 using the slope and the y-intercept. You can push pause on the video if you'd like to try this one on your own. In this case, it's pretty straightforward to see that my slope is negative 1/2, which, again, because I want to think of this as a fraction, change in y over change in x, I'm going to think of this as a negative 1 over a positive 2. You could also think of it as a positive 1 over a negative 2, but thinking of it as a negative 1 over a positive 2 helps because the change in y, therefore, will be down 1. The change in x will be to the right 2. The y-intercept is 0, comma this number, so it's 0, comma negative 1. And that's all of the information I need to be able to graph this line. I've already plotted out the point 0, negative 1, and I know that the slope is negative 1/2, which I think of as negative 1 over a positive 2. So change in y is going to be down 1, and the change in x is going to be to the right 2. So the next point on my line that I'm going to highlight is this point, which is 2, negative 2. Then from 2, negative 2, I can do the same thing. Go negative 1 and a positive 2. By the way, we can do that with any algebraically equivalent fraction. So negative 1 over 2 is also the same as negative 2 over 4. So if you wanted to do a negative 2 over a positive 4, you could. You'd get down here. Also, algebraically equivalent is a positive 1 over a negative 2. So if you wanted to do a positive 1 over a negative 2, that would get you over here at point negative 2, comma 0. You can see that all of these points fall on the same straight line, and therefore I'd connect the dots and extend that line, and here it is. One thing I want to point out about this line is it had a slope that was negative. And as we travel left to right on this line, the y values are decreasing. So a negative slope meant that as you move left to right, the y values are decreasing. Now, that was actually the opposite on our other line from our previous example. Y equals 2x minus 7. The slope was positive, so as I moved left to right, the y values were increasing on that line. So this tells us something about slopes. Positive slopes means that our outputs are increasing as our inputs are increasing. So as x gets bigger, y also gets bigger. A negative slope means the opposite. As x gets bigger, y is getting smaller. So slope is generally telling us the direction that the line is going. An line that is increasing as we move left to right is going to have a positive slope. A line that is decreasing as we move left to right is going to have a negative slope. And if we had a constant line, then the slope would be zero. We wouldn't be moving up or down. So negative slopes means lines are decreasing. Positive slopes means lines are increasing as we move left to right. So I can easily state just by looking at the equation of a line whether or not that line is increasing, decreasing, or constant. Here we have a number of different equations and function equations. The first one, y is equal to negative 2x plus 5, has a negative slope. Therefore, the line will be decreasing. So this is a decreasing line. The second one is f of x is equal to 1/3 x minus 4. The slope here is a positive 1/3, so the line is increasing. Third line, f of x is equal to 2x minus 7, has positive 2 as a slope. Therefore, the line is increasing as we move left to right. Fourth line, y equals negative 1/2 x minus 1 is going to be decreasing because of the negative 1/2 slope. Now these last two may be a little bit harder to see. This is y is equal to 8. You could have also written this as y is equal to 0 plus 8. And that means the slope here is 0, which means that the line is constant. In other words, this line is going to be a horizontal line. Y equals 8 is the equation of a horizontal line. F of x is equal to x minus 3. While it doesn't have, we don't have an explicitly written coefficient out front, anytime we don't have a coefficient written out front, it is an implied 1. Therefore, this function, again, this last function has slope of 1, so the line is increasing. Now, if our lines aren't written in slope-intercept form, we can still find the slope and determine the direction of the line. We just have to use a little bit of algebra. So let's do that with these two examples. We'll find the slope and then we'll state whether or not the function is increasing, decreasing, or constant. For the first linear equation, in order to solve for y, I would start out by subtracting 5x from both sides. And then I would divide by negative 7. If I divide both sides by negative 7, I get y is equal to, well, negative 5 divided by negative 7 gives me a positive 5 over 7 times x. 14 divided by negative 7 gives me a minus 2. So I would know that this linear equation has a line whose slope is 5/7 and whose y-intercept is 0, -2. And that means since this slope is positive, the line is increasing. That is a positive 5/7 forces my line to be increasing. Positive slope, so increase. We have to do a little bit more algebra in this second equation, but not that much more. I would start out by subtracting 3y from each side. If I do that, I get 5y minus 3x minus 9 on the left. And then if I subtract 3y on the right, I get 5x minus 8 on the right-hand side. Then I'd add 3x to both sides. If I add 3x to the left, I get 5y minus 9. If I add 3x to the right, I get 8x minus 8. I'd add 9 to both sides, giving me 5y is equal to 8x plus 1. And then lastly, to get this into slope-intercept form, I would divide both sides by 5. So I'd get y is equal to 8/5 times x plus 1/5. Again, we get a positive slope, and therefore the line is increasing as we move left to right because of that positive slope. Hopefully, you realize that algebraically, to get something into slope-intercept form, basically what we need to do is get the y on one side and isolate it. So isolate the y on one side and then simplify the other side, usually the right-hand side. In this example we just did, we found that the first equation was a line of slope 5/7. And we found in the second equation, our line had slope 8/5. So we had 5/7 and 8/5 as our slope. That's one way we can find the slopes. If I'm given an equation of a line, I can find the slope by writing it into that slope-intercept form. Another way we can find slope is by using the slope formula. Now, the slope formula is a formula we use to find slope when I'm given 2 points on a line. Let's say I'm given points x1, y1 and x2, y2. We know slope is change in y divided by change in x. By the way, the mathematical shorthand for change in y is this delta y, and the mathematical shorthand for change in x is delta x. Remember, slope between 2 points being the change in the y value. Well, mathematically, the change in the y value is just the difference in the y values. So we take y2 minus y1. That becomes our numerator. And our denominator is the change in the x values. So our denominator is x2 minus x1. This is what we call the slope formula. The slope is a fraction which is y2 minus y1 divided by x2 minus x1. In other words, the y value of the second point minus the y value of the first point goes in the numerator. The x value of the second point minus the x value of the first point goes in the denominator. And if we ever have 2 points, we can find the slope of the line based on that. And we don't even have to have the equation for the line to be able to find the slope. We just need to find, or we need to see 2 points on that line. Let's do a couple of examples. Let's find the slope of a line through the given points. Let's say that I know there's a line that goes through the point 2, -4, and also goes through the point -3, 10. And there's a line that goes through the point 8, 3, and also the point 0, -7. These are not the same lines. These are two different lines. Let's find the slope of the line through each pair of points. The slope of this line and then the slope of this line. If you want to try this on your own, push pause on the video. I'm going to write slope as M just as a shorthand because that's what it is when we write it in slope-intercept form. I know it's going to be a fraction. In this first example, I know it's going to be a fraction. The y value of the second point is 10. So I'm going to take 10 and then subtract the y value of the first point, which is -4. That's going to be my numerator, 10 minus -4. My denominator is going to be the x value of the second point, which is -3, minus the x value of the first point, which is 2. This gives me a fraction of 14 over -5. And that's my slope, -14 fifths, or -2.8 if we write it as a decimal. Again, that all came from my slope formula, y value of the second point minus y value of the first point divided by x value of the second point minus x value of the first point. In this second example, we do it the same way. We say we know the line goes through the point 0, -7 and through the point 8, 3. So my y value of my second point is -7 minus the y value of my first point, which is 3, divided by the x value of my second point, which is 0, minus the x value of my first point, which is 8. It looks like this gives me a -10 divided by a -8, which if I simplify that, simplifies to 5/4. So 5 over 4 is the slope of the line that goes through those 2 points. Again, you could make that into a decimal if you wanted. As a decimal, that would be 1.25. So that's how we can find the slope of a line if I'm given 2 points on that line. Now you'll notice that I end up having the slope of this line, and I also know that this line goes through the point 0, -7? Technically, if I wanted to, since I know the slope and I know it goes through the point 0, -7, now I know that the equation of the line is going to be y equals 5/4 x minus 7. The question didn't ask me for the equation of the line in this case, but that's exactly what we're going to do in the next few examples. Let me be more specific. I don't mean the examples right after this one. I mean examples later on in this section. So obviously, we've already graphed using finding a lot of points by plotting a bunch of points. We've also graphed by using the slope and the y-intercept. But another way to graph is by looking at the x-intercepts and the y-intercepts. Technically, a line is only going to have one x-intercept and one y-intercept. So we'll change that to a singular x-intercept and a singular y-intercept because each line will only have one. And let's go ahead and look at how would I find the x-intercept? How would I find the y-intercept? Well, every y-intercept has form 0, y. So to find the y-intercept, all we need to do is plug in a 0 for x and then find the corresponding y value. Similarly, to find the x-intercept, each x-intercept has the form x, 0. So we just plug in a y value of 0 and find the x-intercept. Let's go ahead and do that in this example. Here we have example 8. We're trying to find the x-intercept and the y-intercept, and we'll use those 2 points to graph the line. Here's our line, y is equal to -1/5 x minus 6. I'm going to start by finding the y-intercept. Well, in this case, we plug in x equals 0. We kind of already knew what's going to happen here because this is already in slope-intercept form, and the intercept of slope-intercept form is the y-intercept. So when you plug in a 0, you get a -6. The y-intercept, therefore, is the point 0, -6. Again, we already knew that from earlier because we knew this is in slope-intercept form, and the -6 gives me my y value of my y-intercept. For the x-intercept, we would plug in 0 for y and then solve that. 0 equals -1/5 times x minus 6. And then solving would take a couple of extra steps. I'd have to add 6 to both sides. And then I'd have to multiply both sides by -5. I get -30 is equal to x. That means that the x-intercept is the point -30, 0. So here we have the y-intercept, here we have the x-intercept. If I wanted to find more points, I could, and then I could plot those. But it turns out that because I know the way lines work, that the graphs of lines are completely straight on the Cartesian coordinate plane, I could just connect these 2 points using a straight line, and that would actually graph my line. Let's go ahead and do that. So I've already plotted -30, 0 and 0, -6 on Desmos. You can see those 2 points. Therefore, if I draw a straight line connecting and extending, I would have drawn the graph of that linear equation. So there you go. That is one other way to graph a line. You can not just plug in random points, but you can find x-intercepts and y-intercepts and then just connect the line and extend. Connect those 2 dots with a straight line and extend that straight line out. Again, if you wanted to plug in other values, you could obviously do that as well. If you plug in a +5, you get a -7. And if you plugged in a -10, you get a -4, and so on and so forth. The key point of this problem is more finding the x-intercept and finding the y-intercept rather than actually doing the graphing. Just like the key problem with graphing in slope-intercept form is not the graph itself, but rather finding the slope and finding the y-intercept. Let's do another example where we find the x-intercept and the y-intercept and then use those 2 points to graph the line. Push pause on the video if you'd like to try this on your own. I'm going to do this one now. So to find a y-intercept, again, this is in slope-intercept form, so we know the y-intercept is going to be 0, 10. If there was any doubt, we just plug in x equals 0 and then calculate the value of y, which is obviously 10. So the y-intercept is the point 0, 10. The x-intercept we get when we plug in 0 for y and then solve for x. I would subtract 10 from both sides to start out with. That would give me -10 is equal to 4x. And then I would divide by 4. That would give me a -2.5 as my x value. You can also write that as -10 over 4 or -5 over 2. And that means that the x-intercept is the point -2.5, 0. Let's go ahead and graph the line using just those 2 values. Here's the point 0, 10 graphed on my Cartesian coordinate plane. Here's the point -2.5, 0 graphed. If I connect those dots and extend that, then I get the graph of my equation. So that's the graph of y equals 4x plus 10, the graph of that line. Hopefully that's pretty straightforward. Finding x-intercepts and y-intercepts is pretty straightforward. Just x-intercept, plug in y equals 0, to find the y-intercept, plug in x equals 0. So far in this video, we've always started with equations and found features of lines, or there was a couple of times where we found points on lines and then we found the features of the line. So we were finding slope, we were finding y-intercept, we were finding x-intercept, and we were graphing. And we found points on those lines as well. Now what we're going to do is reverse that. We're going to start with a few features of a line and come up with the equation for that line. Generally speaking, when I come up with the equation for a line, I think of it as y equals mx plus b. So when I write these things, I'm going to write these equations as y equals mx plus b. This is what I kind of alluded to earlier when I said, now that we know the slope and we know it goes through the point 0, -7, I could write the equation if I wanted to. And that's precisely the order of operations that I'm going to do to find these lines. The first thing I always do when I find a line is I find the slope, which in slope-intercept form is the letter m. Then I find the b. That's the y value of the y-intercept. Once I find those two things, then I know the equation of a line has to be y equals mx plus b. And so I just simply write y equals mx plus b, and I'm done. I've found the equation of a line. There are going to be a lot of different ways to find slope. There's going to be really a couple of ways to find b. You could either be given the y-intercept, or we'll see a technique here in just a moment where we plug in a point and solve to find b. So there'll be a lot of different ways to find slope, but really only one way to find b once I have the slope. Let's do an example, and this example is going to emphasize finding that b. So let's find the line with slope of 3 that goes through the point 4, 8. In this case, it's really easy to find the slope because the slope is given to us. We know it is 3. And so the main objective of example 10 is going to be to find the b. So I've found the slope already because it was given to me. Now I'm going to use that to find the b. That and the fact that I know it goes through the point 4, 8. Now, I tend to start out always writing y equals mx plus b at the very top of what I'm doing, because I just, for reference, know that I want to find the equation of the line. So I want to find that equation. I know my slope is 3, so all I have to say is right now I know m is equal to 3. That means my equation is going to look like y equals 3x plus some value of b. Now, since I know that my line goes through the point 4, 8, I know that when I plug in this ordered pair, it's going to give me a true statement. Therefore, we're going to plug in that point. Plug in the point 4, 8. When I plug in 4, 8, be careful that you plug in the 8 into the y value and the 4 into the x value. Since it's a true statement, I know these two sides are going to be equal, and therefore I can solve this equation for b. 8 is equal to 12 plus b. When you subtract 12 from both sides, you get -4 is equal to b. And there I found the b. That's it. Now I know the m because that was given to me. And I know the b because I plugged in that point. So I know that the equation of that line is going to be y is equal to 3x minus 4. Or you could say plus a -4, really doesn't matter. But the equation I'm looking for is y equals 3x minus 4. So that is the technique that we use to find b. There's going to be a bunch of different techniques for finding slope. Obviously, in example 10, slope was given to us. So slope can be found if it's given to us, obviously. Or another way we saw earlier is the slope formula. If I know 2 points on the line, then I'm going to be able to calculate the slope using this slope formula. And then once I found the slope, then I can plug in one of those points to find the b. Let's do an example that uses that technique. Let's find the line, that is, find the equation of the line, going through points -3, -1, and 2, -11. If you want to try this on your own, you can push pause on the video. Like I said earlier, this is just me. You don't have to always do this, but I always like to write y equals mx plus b first just to know what we're looking for. And then I say, let's find the slope. I always find the slope first and then use that with a point to find b. So slope, using the slope formula, this y value of my second point, I'll call 2 -11 the second point. So the y value of my second point is -11. The y value of my first point is -1. So -11 minus -1 goes into the numerator. In the denominator, we're going to have the x value of my second point minus the x value of my first point. That's going to be 2 minus -3. So this gives a fraction of -10 divided by a +5. Simplifying that gives me a slope of -2. That's the simplest way I can write the slope. This means my equation is going to look like y equals -2 times x plus b. And then I can plug in a point. Now, actually, I'm given 2 points, -3, -1, and also 2, -11. It doesn't matter which point I use. If you use -3, -1, and I use 2, -11, we'll get the same b value, or at least we should. I'll plug in the point 2, -11 and do it that way. Remember, -11 is the y value, so I get -11 is equal to -2 multiplied times +2 plus b. So -11 is equal to -4 plus b. Adding 4 to both sides gives me a b of -7. And that's it. Now I know my m. Now I know my b. Therefore, the equation of the line that I'm looking for is y is equal to -2x minus 7. Now, one way to check that this equation is the right one is to plug in both pairs of points. Plug in the first point, see that it gives you a true statement, and then plug in that second point and see that it gives you a true statement. If you plug in -3, -1, and then simplify, you should get a true statement, which in fact you do. And if you plug in 2, -11, and then simplify, you get a true statement. So that is one way you can check your answer, is just by plugging in both those original points and seeing that you get a true statement. Let's try another one. Let's say that we want to find the line going through points 9, 2 and 5, 7. Go ahead and push pause on the video if you'd like to try this on your own. In a couple of seconds, I will do this. All right. So the first thing I do is find the slope. Always find the slope first. We have 2 points, so I'm going to use the slope formula. The numerator is going to be 7 minus 2. That's the y value of the second point minus the y value of the first point. And then the denominator is going to be 5 minus 9 because that's the x value of the second point minus the x value of the first point. This gives a slope of 5 over -4. Or you could have also written this as -5/4. Either way is fine. Now I know my equation is going to be y is equal to -5/4 times x plus b. In order to find the b, I just need to plug in one of those points. I'm going to plug in the point 5, 7. You could have also plugged in the point 9, 2. Either way is perfectly fine. We would get 7 is equal to -5/4 multiplied by 5 and then plus b. -5/4 times 5 is -25/4. Therefore, I get 7 is equal to -25/4 plus b. And then I'd have to add 25/4 to both sides. Now, if we use improper fractions, Then when I add 25 over 4 to both sides, I'd get 53 over 4 as my value of B. So therefore, my equation is going to be y is equal to negative 5/4 x plus 53 over 4. Now that's my equation using improper fractions. Obviously, if I wanted to, I could have written that equation utilizing decimals as well. Negative 5 over 4 is the same thing as negative 1.25. 53 over 4 is 13.25. Both of these are the same equations, so it doesn't matter how you write those down. Obviously, if you're writing them down for a particular homework problem, it may ask you to write those in a certain form, whether it's an improper fraction or a decimal or a mixed number. But those are the same two equations. So not every time are we going to get really nice numbers for our slope or for our B. Now, these tools that we're using here, I want to mention, can be used in word problems as well. And if you're dealing with word problems and linear modeling or modeling with linear equations, then these are going to be very, very useful tools. You know, finding the slope, being able to create an equation of a line, and so on and so forth. We're not going to go over that in this video, but in the next video or in another video, we'll look at word problems with linear equations. So now we have a couple of different ways to find slope. Slope could be given to us, or we could find the slope using the slope formula. We plug in a point to find B, and then we get our equation. We're going to go over a couple of other ways to find slope as well. And those couple of other ways are going to be in reference to parallel and perpendicular lines. Two lines are parallel if they have the same slope. So we say two lines are parallel if they have the same slope. Two lines are perpendicular if their slopes are negative reciprocals of each other. So if I write one slope as the fraction a over b, then a perpendicular slope would be one that is negative b over a. So reciprocal means we change numerator and denominator, and then negative obviously means one is negative, one is positive. Now, most pairs of lines, I want to say, are neither parallel nor perpendicular to each other. So I don't want to give you the impression that if you're given two lines, they're always going to be parallel or they're always going to be perpendicular. There's lots and lots and lots of pairs of lines that are neither parallel nor perpendicular. But if we have parallel lines, because they have the same slope, if I know one line is parallel to another, I can find the slope knowing that it's the same. And if I have two lines, one of which I know the slope of, and the other one I know is perpendicular to the first, then I can use the fact that the slopes are negative reciprocals to find the other slope. Before I jump into doing some things algebraically, I just wanted to talk about the graph of parallel lines and the graph of perpendicular lines, because this is something that may come up later on in your mathematics. So we said parallel lines have the same slope, something like y equals 4x plus 10 and y equals 4x minus 1. Well, if these two lines have the same slope and they're not like the same line, then these two lines are going to continually move in the same direction. And therefore, these parallel lines are never going to cross. They're always going to stay a little bit away from each other. So that is really the interesting feature about parallel lines, is we have two lines moving in the same direction and they never cross. And that's all because they have the same slope. Now, if I take perpendicular lines, so let's say one of my lines is y equals 4x plus 10, and my other line is y equals negative 1 over 4x minus 10. So the slopes are minus 1, excuse me. The slopes are negative reciprocals of each other. One is 4x, or one slope is 4, the other is negative 1/4. Now, what's special about perpendicular lines is where they cross. This place at which they cross is actually a nice intersection because these two lines are meeting at 90-degree angles. So perpendicular lines meet at 90-degree angles. It might be hard to see on this one, but these are perfect 90-degree angles. And that's what's interesting about perpendicular lines when I graph them. Perpendicular lines meet at 90-degree angles. Parallel lines never touch. And obviously, there's lots of examples where lines intersect, but not at 90-degree angles. Here's an example of that. Y equals negative 1x minus 1 and y equals 4x plus 10. So those intersect, but not at 90-degree angles. In this section, we're not going to deal a lot with the graphing of parallel and perpendicular lines, but we're going to focus on the slopes of parallel and perpendicular lines. So that's our focus for this section. Parallel lines have the same slope. Perpendicular lines have slopes which are negative reciprocals. And any other combination, then the lines are neither parallel nor perpendicular. Let's take a look at this example. We have a bunch of pairs of lines, and we're going to decide whether each pair is parallel, perpendicular, or neither. If you want to push pause on the video and do this, then go ahead and do that. I'll do it in a couple of seconds. Now, every line that is on these examples is already in the slope-intercept form. We have y equals 4x minus 2 and y equals 4x plus 9 as my first pair. Both of those are already in slope-intercept form. The slope of line 1 is 4, and the slope of line 2 is 4. Pretty easy to see that both slopes are 4. And because both slopes are 4, then the lines are parallel. Again, both slopes are 4. In this second pair, one slope is a positive 1/3 and the other slope is a positive 3. So these lines have reciprocal slopes, but they're not negative reciprocal. They're clearly not parallel lines because they have different slopes. But they're also not perpendicular because the slopes are not negative reciprocals. So the lines are neither. That is neither parallel nor perpendicular. And that's because one slope, actually, let's just write M1, the slope of line 1 is 1/3, and the slope of line 2 is 3. This last pair is where the lines are perpendicular. The slope of line 1 is -2. And the slope of line 2 is a positive 1/2. So these two lines are perpendicular, they're negative reciprocals. Realize that when you take the reciprocal of 1/2, you get 2/1, which is a 2. And when you take a reciprocal of something like a -2, it's -1/2. So the negative reciprocal of -2 is going to be a positive 1/2. The negative reciprocal of 1/2 is going to be a -2. Hopefully that makes sense because -2 is the same thing as -2 divided by 1. Let's look at another example and decide whether these two pairs of lines are parallel, perpendicular, or neither, and whether these two pairs of lines are parallel, perpendicular, or neither. If you want to try this, push pause on the video. In these cases, it's probably easiest if I just rewrite them both into slope-intercept form, and then I can easily get the slopes for each line. So if I rewrite this first one into slope-intercept form, I would subtract 5x from both sides. That would give me -9y is equal to -5x plus 4. And in this second equation, we would subtract 2x from both sides, giving me 8y is equal to -2x plus 12. One more step in each equation. We'll put these in slope-intercept form. In the first equation, I'd have to divide both sides by 9. Not 9, -9. So dividing both sides by -9 gives me y is equal to a positive 5/9 times x minus 4/9. And the second equation, I would have to divide both sides by 8. that would give me y is equal to negative 2 over 8, which is negative 1/4, times x plus 12 over 8, which is 3/2 reduced. In terms of the slopes, it's pretty easy to see that one of the slopes is 5 over 9. The other is negative 1/4. They're not negative, one is positive, one's negative, but they're obviously not reciprocals, so they're not negative reciprocals of each other. They're obviously not the same. And so in this case, the lines are neither. That is neither parallel nor perpendicular. I do the exact same thing in this second example. I want to isolate y. I'd probably add 6y to both sides and then subtract 2. That would give me 6y is equal to 2x minus 2. And then for the other line, that's already in slope-intercept form. I don't have to do anything with that. Dividing this first line on both sides by 6 gives me y is equal to 2 divided by 6 is 1/3, x minus 1/3. And the other line is, again, y equals negative 3x plus 10. So one slope is 1/3, the other slope is negative 3. Those are negative reciprocals of each other. And therefore, these lines are perpendicular. These two lines are perpendicular. Notice that in order to determine perpendicular versus parallel versus neither, I really don't care what these values of B are. The only thing I'm focusing on is the slopes. If the slopes are the same, like we had up here, then the lines are parallel. If the slopes are negative reciprocals of each other, like we had in this example and also in this example, then the lines are perpendicular. And if the slopes are neither the same nor negative reciprocals of each other, then we say the lines are neither parallel nor perpendicular. Now we're going to go back to finding lines. So as always, we want to find the slope first, then find the b by plugging in a point, and then write y equals mx plus b. Now that we understand what parallel lines are and perpendicular lines are, we can also find the slope using parallel lines or perpendicular lines. So let's do an example that highlights that. Let's find the line which is parallel to y equals 3x minus 7 and which goes through 0.51. All right, so we want our line to be parallel to this one. Now this one, I want to point out, has slope of 3. So because that one has slope of 3, then my line also needs to have slope of 3. So my line is going to look like y is equal to 3x plus b. We're going to plug in the point 5, 1 in order to find the b. Remember, 1 is the y value, 5 is the x value. I get 1 is equal to 15 plus b. Subtracting 15 from both sides gives us that b has to be negative 14. So I found the slope using the fact that our line is parallel to this one, and then I found the b by plugging in my point, as always. Notice that I did not use the part of this line, the -7 part of this line. That doesn't come into play. Knowing that it's parallel to this one only gives me the slope. The -17, I could have just as easily had written -17 as -7 or -27 or -78. Who knows? But the point there is that we're not using that part of the line. The only part of the line we care about of the one that I'm given is the slope, which in this case is 3. Now that I know the slope and the y-intercept value, then I can write down the equation. The equation for this line is going to be y is equal to 3x minus 14. So there you go. Parallel lines have the same slope, and so we just use that fact to find the slope of the line I'm trying to find. Let's do another example. Let's find the line which is perpendicular to y equals 1/4 x plus 12, and which goes through the point 3, 10. If you want to try this on your own, pause the video. I will do this in just a couple of seconds. On this one, we're going to have two slopes. So I want to point that out, that here the slope of the given line is equal to 1/4. So the slope of that given line is 1/4. That means the slope that I'm going to use has to be the negative reciprocal of 1/4. So I'm going to take negative, and then I'm going to take the reciprocal of 1/4, which is 4/1. So my slope needs to be -4. Therefore, I know my equation is going to look like y equals -4x plus b. And I can plug in the point that I'm given. I know my line goes through the point 310, so let's plug in that point. That'll give me a true statement. That leads me to seeing that 10 is equal to -12 plus b. Adding 12 to both sides gives me a 22 as the value of b. Now I've found my slope of -4. I know b is 22. And so the equation that we're getting is y is equal to negative 4x plus 22. So there we go. And that's it. That's what we're asked to find. We're trying to find the line which is perpendicular to this one and goes through the point 310. And that line happens to be y equals negative 4x plus 22. Let's do one more example like that. Let's find the line which is perpendicular to y equals negative 5x plus 4, which goes through the point 10, comma, negative 18. So we're going to find a line which is perpendicular to y equals negative 5x plus 4, and which goes through the point 10, 18. Push pause on the video if you'd like to try this on your own. All right, so in this case, my line is already in slope-intercept form. The given line is in slope-intercept form once again. The slope of this given line is negative 5. And so my slope needs to be the negative reciprocal of that, since my line needs to be perpendicular. So I always write y equals mx plus b. I'm saying my slope has to be the negative reciprocal of negative 5. That's like negative 1 over a negative 5, which is a positive 1/5. So my slope should be a positive 1/5. That tells me my equation is going to have the form y equals 1/5 x plus b. And then I can plug in that point of 10, 18 in order to find my b. Again, remember y value is 18, x value is 10. So we get 18 is equal to 2 plus b. Subtracting 2 from both sides gives me that 16 is equal to b. And now I have both the slope and the b, which means I have everything I need to write down the equation. My equation is y is equal to positive 1/5 times x plus 16. Now, in each of these problems that were given to us, when we found the slope of a line that was perpendicular or parallel to a given line, the given line was already in slope-intercept form. Obviously, if the given line is not already in slope-intercept form, then we'd have an extra step of changing it into slope-intercept form to identify the slope. We've done that a couple of times earlier in this video, so I'm not going to go over that now. But if my lines weren't in slope-intercept form, I'd want to change them into slope-intercept form in order to find the slope quickly. But other than that, that's the idea. You can see that in each one of these cases where we're finding a line, we always start by trying to find the slope first, plug in some number, plug in some point, and that will give us our numerical value for b, and then we just write the equation. There were a lot of different problems and different examples in this video on linear functions and their graphs. We graphed in multiple different ways. One was by plotting points, one was by using the slope-intercept form. One was by finding the x and y intercepts. We looked at the slope formula, and then we used those features to find the equations of lines as well, along with the features of parallel and perpendicular lines. So this section was a lot of material on linear functions and their graphs, but it's over now. So that was the end of our video, and we'll do other problems featuring linear functions in other videos.